This video is sponsored by Tyler Boone, the founder of TI Projects. His high-quality titanium design skills have brought beautiful custom merchandise across the blockchain sector. The Guardian Arc Plate is a solution for self-custody. It helps keep your private keys safe and protected. Fireproof, waterproof, future-proof. I couldn't have had a better sponsor for this important video. Click on the link in the description and watch for his newly designed accessories that are coming to the Wave of Innovation, the XRP conference in Australia this March.
Hey everybody, super excited to be on here with you all today. A huge part of our business is focused around how to make blockchain secure. So just at a high level, BTQ was founded in 2021 by a group of post-quantum cryptographers with the goal of setting out to make sure that all of the digital infrastructure that we have doesn't go obsolete when quantum computers come on the scene. And it seems like more and more every day that there are huge developments in the space of quantum computing. So it's really just a matter of time. And so our team sees this as a kind of time management issue where we are trying to kickstart transitions as early as possible. We do this by building kind of solutions in both hardware and software. So as Eri said, we work with we are currently participating in the NIST standardization contest, which is the U.S. government standardization body, and they've set out some standards for post-quantum algorithms. These are algorithms that are resistant to the computers that we have today, but then also resistant against quantum computers. So these will be algorithms that will be secure centuries into the future. So we're currently participating in the NIST round for additional signatures to be standardized. I'm currently here in Taipei, Taiwan, and here we do work. We manufacture chips, so we implement these standardized algorithms into hardware and optimize them, and then we also do a lot of work around software and particularly around blockchain. So applying these post-quantum digital signatures into blockchain, and not only just applying them, but then also figuring out how to scale them, how to make them more compact, so that we don't lose all of the wonderful scaling efforts that we've been able to achieve in the past few years in blockchain. So yeah, that's a high level, and I'm super excited to speak to you all. There's a few teams in this space who are working on post-quantum cryptography, and you have a lot of the big tech firms who are looking at this, and some larger players as well in the US. And so the niche that we've carved out for ourselves are, how do we implement PQC in resource-constrained environments? And these are still mission critical because these you can think of as edge devices, IoT devices, chips that go into satellites. So anything that operates, that doesn't have access to massive amounts of compute via data center, or may not be, hooked up into landlines or Ethernet. Those are the types of devices that we focus our PQC implementations in. And this also fits really well with blockchains because, in a blockchain you have several nodes that are all decentralized, and no one node presumably has a ton of power, maybe not the amount of power that big tech firms have to expend on making sure that all of their digital infrastructure is secure. So the way that we go about this is by building software and hardware that's optimized for these types of resource-constrained environments, and we do this in a few ways. Maybe we can jump into those a little bit later, but that's the idea. On the hardware side, what we do is we implement our algorithms in a new type of architecture. So many of you might know the Apple M1 MacBooks, or now they have M2s and M3s, but they have this kind of integrated memory component in them. And this has been a pretty big breakthrough when it comes to laptops and computational power. The idea here is that is that you kind of abandon the traditional von Neumann architecture, and this has kind of like, you can think of it as like topologically separated units for CPU, RAM, and disk. And essentially, every time you compute something, you need to shuttle data through a bus into the processing unit or into RAM. And all this takes a lot of energy, and it also creates a lot of latencies. And so the breakthrough architecture that Apple's using and now that we're using for post-quantum cryptography is what's called compute in memory. So the idea is that you bring all of the compute or as many computing processes as close to memory as possible, and some are physically inside the memory. So you kind of have this embedded processing unit within a memory allocation, and then you're able to save on all of those data movements between those two topologically separated components in the previous architecture. So that's how we approach the hardware problem is by using this compute and memory approach. And on the software side, here we try to take advantage of proofs of knowledge. So a lot of blockchain, or especially if you're in Ethereum, you might have heard of zero knowledge proofs and the like. So the idea here is that you can essentially you can perform similarly heavy computation somewhere else, and then prove that you can prove to someone else that it was correct, it was done correctly, very cheaply, in typically logarithmic complexity compared to what it took to generate that, to actually expend that computation. So the idea is that you can compute on something very difficult in a place that it's meant to be computed on, and then you can prove that it was done correctly elsewhere. And this is how we approach like blockchains, for example, or scaling PQC, post-quantum cryptography, in blockchains, where we can essentially validate signatures. We can validate that data has been encrypted and it hasn't been broken, and that all of the data is being transferred to the appropriate sender without being compromised. We can do all of this using these post-quantum zero-knowledge proofs. So the idea here is that we kind of wrap it up we wrap up all the important information in a proof, and the receiver or anyone else in the network can act as a verifier to make sure that all of the data is indeed true, without having to expend all of that heavy post-quantum cryptography on that data in transit.
Yeah, it's interesting too, because I know when we think, when I think zero knowledge proofs in the context of how blockchain or distributed ledger is going to leverage those proofs, I always think like the minimum amount of information needed to facilitate some sort of a task or an access point, things like that. So is that kind of, from the post-quantum standpoint, is it kind of similar in that way, where you're taking really heavy kind of data processes, wrapping them, and then whoever's actually wants access to the data, it's based on just whatever level they require access at from the zero knowledge proof standpoint, and then you build it up or you scale it up depending on how much access they need or whatever it may be.
Yeah, exactly. I mean, that's a super well summarized idea. So basically, like, as it's actually, it's kind of interesting in the U.S. as well. The White House has kind of, in response to this quantum threat and all of these standardizations that they're doing around post-quantum cryptography, they're rolling out and advising U.S. companies and organizations to follow what's called a zero trust architecture. This is also coming up at the BIS that we were at last week or a couple of weeks ago. And I'm seeing it in more and more circles, this idea of a zero trust architecture. And the premise of this is that, even if you're an American company talking or interacting with another American company, you can't assume that they haven't been hacked or that they haven't been compromised. And so the idea is that you convey as little information as possible to your counterparty, and that you essentially have you use minimal trust assumptions when interacting with them. And that's the whole idea of in these zero knowledge proofs as well, where you essentially distill all the information down into a set of facts that we can prove about the information, and we can relay that across the network. And even if even if something in the worst case were to happen to that data, it would only expose a tiny fraction of all the actual sensitive data that went into generating that proof.
Yeah, I'm going to go off script just a little bit here, Eri, from the questions too. I know we've got the next one down below, but the zero knowledge proof stuff's really interesting to me, especially when you start considering that the way that technology is growing and growing, and the way that, I mean, I believe that zero knowledge proofs are going to start integrating in with the digital identity plays as well. Have you guys kind of worked in any aspects of digital identity aspect, or what are your thoughts around zero knowledge proofs or post quantum cryptography dealing in zero knowledge proofs that do deal in digital identity as well? Because you mentioned the least amount of information necessary to kind of participate in whatever you're trying to participate in. Do you see that play? Do you see digital identity aspects playing a role in that as well?
Yeah, great question, and definitely. So we do a lot of work with DID, one of our closest partners. The name is Holonym. If you're interested, they for example, they're part of the onboarding process for Gitcoin, but they do DID, and we provide them with essentially the tools to build post-quantum zk-SNARKs to underpin their DID service. But absolutely, like, ZK is super important when it comes to decentralized IDs, identifiers, in case we hadn't thought that out yet. But DID stands for decentralized identity, and the idea here is that you can wrap up your driver's license or your passport or your driver's or other forms of government issued ID, and you can generate proofs that you're either a U.S. citizen, or that you're you live in this state, or you reside in a certain state, or that you're over a certain age. And the idea of ZK here is that you'll scan your passport, say that you're a Canadian citizen, but whoever verifies, whoever checks that, whoever wants to check this proof doesn't see any information in your passport at all. And so ZK is super important when it comes to kind of interacting with the rest of the world using our sensitive information. Something that isn't really status quo right now. When we do KYC, all of our information is absolutely disclosed and it's held somewhere that it's likely going to be hacked. Actually, there was just a hack in India where I think 84 million people's government issued IDs just got blown out into the water. So it's a huge problem, and this is really a perfect opportunity for ZK to step in. And that's really what we're focused on at BTQ is not only having these nice pieces of cryptography to use, but then making sure that they're to the highest standard of security.
Reading through the BTQ blog, you guys discussed the transition to post-quantum cryptography. And I should mention, we always do this in all the spaces, but if there's we always try to keep it like as simple as possible. So PQC, post-quantum cryptography for anybody down there listening. In the blog, you guys discussed what the transition to post-quantum cryptography looks like, or what it may look like. Can you educate the audience a little bit about that transition from the way the cryptographic standards are today, and that transition into post-quantum cryptography? And for the audience, I mean, for everybody in here, why it matters to all of us?
Yeah, for sure. So cryptography, just at a high level, this is the idea of encrypting and decrypting sensitive data. And the idea of this is that we want to be able to communicate to each other without having someone in the middle, sit in the middle of our networks and pick apart all of our packets that we're sending to each other, and then decrypt all of our data. So in cryptography, the idea is that you want your recipient to be able to read the data, and you want nobody else or any unintended party to not be able to read the data. And so most of the cryptography that we've implemented in our tech infrastructure today, it relies on what are called these. So there's the idea of a public key cryptography, which essentially allows you to sign your data using your private key, and then allows anybody to check that data came from you using your public key. And all of these crypto systems were built under the assumption of the difficulty of certain mathematical problems. And these were largely devised in the 70s and 80s. And they were standardized based off of the assumption that our computers would never reach a certain threshold, and they would never get so powerful, so that we could take a relatively conservative approach to encrypting our information, so that all of the interactions still stay relatively efficient. And that this assumption is now being broken with the advent of quantum computers. Quantum computers had always been around, especially they were first theorized in the 80s or 90s, but in the past couple of decades they've made some significant traction. And the first quantum algorithm just so happened to be it's called Shor's algorithm, and this happens to be the one algorithm that breaks all of the cryptography that we rely on. So Shor's algorithm is an efficient way to find to factor large prime numbers, and also to solve the discrete logarithm. And those are the problems that we assume to be difficult underneath our crypto systems. And so what's needed is now this jump to what's called post-quantum cryptography, this transition to post-quantum cryptography, so that we can replace all of our digital infrastructure, all of our security infrastructure, so that they rely on different problems apart from the factoring of large prime numbers and the discrete log problem. This is what's prompted the US government to launch this standardizations effort. Again, this is the National Institute of Standards and Technology, NIST, in the US. And in 2021, back in 2017, they launched this project, and it took them about 5 years to come to consensus on what these safe post-quantum cryptographic algorithms are. And that's where we sit. We've just released we've just heard the standards, and we now have the chance to implement them. But yeah, something that sets us apart is we made a bet in 2021 that certain algorithms would be standardized, and so we started optimizing them before they even became standardized, and it just so happened. We made an educated guess based off our expertise, and we were correct, and so we've been optimizing these NIST standardized algorithms for coming up to 3 years now, when they only got standardized earlier this summer.
Awesome. Can you maybe discuss what you mean by crypto agility and why it is so important for these ecosystems to start, if they haven't done so already, developing it?
Yeah, definitely. So crypto agility refers to the ease of which the ease of switching to more secure cryptography once the currently implemented cryptography goes obsolete. And there's several ways that teams can go about this. In Ethereum, for example, they now have account abstraction, where they're able to implement wallets using different types of cryptography. So it's not all based off the same elliptic curve cryptography. And that's one nice method where you can have, we like to frame it as having a quantum safe savings account, where you store most of your crypto, but then it's a little bit more expensive just because it has PQC, and PQC tends to be a little bit more expensive on blockchains. And then you can have your elliptic curve, your pre-quantum checking account, where you do most of your trading and transactions from. You can just funnel money from your savings account to your checking account. And so that's one way that chains can move towards, or to be more crypto agile. And really, the most important thing is that teams and chains have some mechanism in place where there isn't a huge gap between having these pre-quantum cryptographic primitives and then implementing and using those post-quantum crypto primitives, because in that time that would be plausibly enough time for a quantum adversary to come in and drain everybody's accounts. And again, the way that these quantum algorithms work is that they're able to essentially derive private keys using a public key. And every blockchain account consists of a private key and a public key. All of your Bitcoin and Ethereum, those are all stored using your private key, and your public key is by nature public. And so everyone's public keys are out in the wild as soon as you make a transaction, and those will be they're their private keys, their corresponding private keys, will be at risk if these chains aren't crypto agile. Crypto agile also refers to being flexible enough where you can swap in cheaper or more efficient, essentially cryptographic mechanisms, so that people aren't paying such exorbitantly high gas fees like they were in Ethereum and the peak of the bear or the bull. And so there's always going to be this kind of tension between picking something, settling down with it, but then having a flexible enough system so that you're able to improve, at least in terms of quality of life, and then also make that jump if you're facing an existential threat like quantum computers.
The one thing that I remember having a conversation with Chris, which really stood out, is that to be post-quantum ready, the signatures, I guess, become very long, right? And in becoming long, I remember you saying you have to kind of compress that down to make the latency not so crazy, because right now we fit so much in a block, but if we long signatures that come in the future, you can only fit so many in the block. So if we have some chains that are slow now coming to consensus with these long signatures, you said that there could be an enormous weight because they're not compressed. But you have this product. You have a product called BTQ scale, I believe it is.
Yeah.
And that, and that was fascinating to me, that you can make these signatures, I don't know if I remember right, something like 27 times smaller. Exactly. Yeah. So that you can continue to come to a consensus within that block size that still keeps it very close to what we're doing now. But if we don't do that, if you don't have that compression, I guess I talk about a world of post-quantum. If you're not compressing these signatures, what does that look like for the blockchains out there?
Yeah, definitely. So these NIST standardized algorithms that are deemed secure. So there's NIST to standardize 3 algorithms, and of the 3, the smallest algorithm has a signature length that is 10 times the length of what's currently being used today in blockchains, and the largest one is over 1,000 times larger. So let's just stay with the simple case where we just implement kind of naively these the smallest NIST standardized signature will have transactions that essentially have a signature appended to it that gets sent on into a block. And because these signatures are 10 times larger, you effectively have something around 10 times fewer transactions being fit into a block. And this creates essentially bottlenecks where, as a user, we're paying either 10 times higher gas fees in order to get the same processing time, or we're just waiting 10 times as long. So our settlement and finalization, if we're executing a trade, we might be 10 times behind the ball than further behind the ball than we are today. So this obviously presents a huge problem for blockchain. It solves the existential risk of quantum computers just wiping out our private keys, but it doesn't solve the risk of quality of life, user experience, and just overall utility of the blockchain if it's 10 times slower. And so for us, it isn't enough to just naively implement these post-quantum signatures, but then also figure out ways to scale them. And that's exactly what you were talking about, Eri, where we compress these signatures so to give you some numbers, we can compress thousands of post-quantum digital signatures so that they're the same size as a single signature. And so we get orders of magnitudes of savings using this type of compression so that we can have security, but then also have trading and DeFi and all of the other wonderful things that we have on chain right now.
Can you just talk about some of the actual work that you've done for the Ethereum network?
Yeah, for sure. Yeah, so we've worked with several L2s in Ethereum, most notably of which is one of which is Starkware. They're one of the largest zk companies in Ethereum, and what we did with them is we implemented this PQ scale so that we're able to aggregate signatures on Starkware. Kind of the whole grand scheme of future-proofing Ethereum is kind of consolidating into this idea that we have. We're calling it layer Q, and this is going to be this test bed for post-quantum Ethereum. So what we've done is we've forked Ethereum, and we kept all the great parts of it, but we swapped out all the vulnerable cryptographic primitives, namely all of the elliptic curve algorithms, and we put in the NIST standardized algorithms, and then we kind of made it more efficient by layering on this PQ scale. And what we've done here is we actually put PQ scale into the L1 itself, so it's baked into the blockchain. So it's like the engine that drives all the transaction processing. And what we'd like to do now is open this up to the world and say, look, this is the first feasible demonstration and a practical demonstration of post-quantum cryptography in Ethereum. And we'd like to bring this closer to the community by writing Ethereum improvement proposals, one of which we have drafted, and essentially getting more teams on board with not only using these primitives, but then also using the scaling that can come with it so that they can integrate the security into their applications without forfeiting a lot of the user requirements.
Polarizing points, obviously, of proof of work, especially when you get into hash rate and Bitcoin is, effects on the environment, energy, things like that. Even with some of the green initiative things that we hear about mining potentially coming down the pipeline, but quantum sampling and proof of work slashing blockchain energy use by 1,560 times compared to the current proof of work system. Can you maybe expand a little bit on what quantum sampling is and how that might play a factor into some of these ecosystems that maybe proof of work?
Yeah, for sure. Yeah. So when we took a look at Bitcoin, for example, and we looked at the proof of work there's two problems. One is that the hash function underpinning the proof of work is not quantum resistant. So if a quantum computer were to come along, they'd just be able to mine every block faster than everybody else, and then kind of steer the chain in the direction that they wish. So that's the first problem. The second problem is that it's also extremely energy inefficient. And yeah, there's been some numbers I'm sure many of you are familiar with, where Bitcoin uses the same amount of energy as like the 9th largest country in the world. And so when we thought about how we can upgrade the security of Bitcoin, we wanted to solve both of these problems. So what we did is we implemented a quantum sampling problem to essentially replace to create the new proof of work. So you demonstrate proof of work by performing this quantum sampling problem. And this makes it resistant to attacks by other quantum computers because the problem is inherently quantum. And then it also happens to be far more efficient than the proof of work, because essentially all you have are these very tiny little, they're like the size of a microwave. They're called boson samplers. And really all they do is they shoot little beams of light through these beam splitters. And that is enough to create the sampling problem. And so that's why we have, it's several orders of magnitude savings in energy efficiency. And also, meanwhile, being quantum resistant. We had several discussions with the Bank of Canada on their work in central bank digital currencies, what are called CBDCs. And I guess just to preface to this, every major country has several CBDC projects ongoing. And then the BIS, the Bank of International Settlements, they also have 10 projects in investigating CBDCs as well right now. So they're of huge interest and kind of a natural, I guess it seems like the natural evolution. It's just the digitization of the financial ecosystem. And so Canada is looking at deploying CBDCs in different models, and I think they want to be. My intuition is that they want to make sure that they're appealing to the public, so that they're not kind of imposing this his electronic currency that, you know, a lot of people have their reservations about CBDCs because they think they'll be tracked, and it's the government's way of kind of reining in power and consolidating it so that they're able to control everyone and everything. But I think that leaves out the assumption that leaves out the possibility of having private transactions in a CBDC model. So just as we can kind of exchange fiat in cash hand to hand without anybody knowing, the same kind of the equivalent process can happen in a CBDC as well with these private transactions, where I can send Eri some crypto, some CBDC in Canadian dollars, but no one will ever know. No one will, unless it gets hacked by a quantum computer. But this is why PQC is important in this aspect. But yes, the Bank of Canada was looking at essentially anonymous wallets and private credentials for CBDCs, and it seems like it was a huge priority of theirs, which I'm really interested about, which I'm really interested in. And so we're trying to help them figure out ways to have this anonymous credentials, but then also have it to be post-quantum as well. We are currently participating in the latest round of the BTQ post-quantum cryptography competition. We submitted a new signature scheme that stands in a category of its own. So this is specifically what the NIST is looking for. They have already standardized 3 algorithms. 2 of them come from a family of what are called lattice-based cryptography, and the 3rd one comes from what's called hash-based cryptography. And what the U.S. government is now looking for is to diversify the algorithms that they'll standardize next. The reason for this being, if one family turns out to be compromised, we'll have other families of cryptography to choose from. And so we submitted this. We submitted our submission is called Prion, and it stands in a category of its own. And in the first 30 hours, there were 4 other submissions in addition to ours, and all of those got broken except for ours. So we stand alone in our category now, which we're very excited about. And we did this in conjunction with Foxconn, or Hanhai Research Institute, as well as some really prestigious university researchers from Georgetown University in the U.S. and more so in Taiwan. So we're very excited about this, and that's what we'll be presenting again at this cryptography conference tomorrow. Our work on Prion. So we're looking to deepen our collaborations with Foxconn and Hanhai Research Institute. So we're working on some initiatives with also in conjunction with the Canadian government, specifically the scientific funding body in Canada, to continue looking at implementations and optimizations of these post-quantum algorithms and hardware. And on the blockchain side, we're looking to really kickstart this transition and to help teams get their bearings on what the landscape is like, what are the options that they have in front of us, and provide solutions so that they can become quantum resistant. We set out to investigate post-quantum algorithms, and we've since come up with a new proof of work protocol using PQC that's as we said, more efficient than Bitcoin and also more safe. And we've had the submission to Prion, and we've released several academic papers. And so I think we've been really proud of our academic achievements, and we're now starting to get some recognition and looking at how do we productize a lot of this research. And I think those are some of the upcoming milestones that we'll be looking at. How do we get feedback from the community, feedback from other researchers and companies to implement a lot of this research into production, and just to continue building and try to do good work. Anastasia is also a fantastic head figure. She hosts our podcast where we have some of the brightest minds join us. This is specifically around post-quantum cryptography and quantum computing. And Anastasia has a great background in physics. So she's super well versed in all of that. So if you're looking for audio content, I would highly recommend the podcast. Definitely follow us on Twitter. Also reach out to me if you have any questions. I'm more on the product side. So if you have ideas or if you just have general inquiries, happy to walk through those with you. Just this is my passion. I love talking about this stuff. So I'm happy to talk with anytime.